We now turn to the development of quantum mechanics, not the old quantum theory, just with its stationary states and its complicated Ptolemaic-like extension of that in new ways, but rather a really fundamental new look at what the basic concepts of nature should be. We'll proceed in 3 steps. First, we'll look at Werner Heisenberg's discrete analysis of what he called his matrix mechanics, or what came to be known as matrix mechanics. Then Erwin Schrödinger's continuous theory of the quantum, and then the synthesis of these 2 very different approaches by 2 very different scientists in the Copenhagen interpretation, the standard way of understanding quantum mechanics that survives to this day. Heisenberg and Schrödinger couldn't have been more different. Heisenberg was an enthusiastic outdoorsman, conservative politically. He was sort of a outdoor scout type in the youth organization that would take hikes up in the mountains to rebuild a new Germany after the failures of World War I. He was somebody who was deeply interested in physics from early on, but never particularly adept at complicated calculations, yet tremendously intuitive and productive in new ways of thinking about physics. He started with Bohr's ideas, this idea of the stationary state, but then without the notion of a matrix, physicists didn't know what matrices were unless you were a particularly mathematically oriented one, and that was not Heisenberg. But he realized that he could take an array of numbers to calculate the different possibilities for jumping from one orbit to another, not just from going directly, say, from orbit N to orbit M, but what if you went from N to K to M, or N to K to L to M, and he began to sort of quantify and understand the different ways in which the electrons could hop from orbit to orbit without ever talking about the way you got from one to another. In that, he followed Niels Bohr very strictly. Bohr forbade any discussion about what happened between one orbit and the other. There was no way to track it like a classical particle. There was simply being in orbit X to being in orbit Y. So Heisenberg came to see his matrices as codifying measurements, as a measurement of position or a measurement of momentum, extending this idea of Bohr's, of forbidding certain kind of classical talk. So what he discovered was that certain transitions or certain ways of understanding a process that would go from one state to another state couldn't be reversed. That measuring first momentum and then position was not the same as first measuring position and then measuring momentum. In fact, you might think of it like rotating a book or a computer. So suppose I have a book like this and I start Apple face forward, and I have an axis that goes towards you, call it X, and a vertical axis, call it Z. And I rotate around the X-axis clockwise 90 degrees, like so. Then I rotate clockwise around the Z-axis, so I end up like this, the book or computer facing you edge on. But now I could do that in the reverse order. Suppose I start in the same state, Apple facing you, and I rotate clockwise around the Z-axis, and then clockwise around the X-axis as far as you're concerned, and I end up with the short edge towards you. So they're different. So whether I rotate around the X-axis first and then the Z-axis, or the Z-axis and then the X-axis, gives me different results. Well, that's an example of what Heisenberg's talking about, that processes understood as these arrays of numbers that he used to understand quantum processes depended on their order. Well, this was very interesting and was utterly unfamiliar from classical physics. In classical physics, if I measure the position of a marble and then its momentum, I could just as easily do the other way around and measure its momentum and then its position. It makes no difference at all. In quantum theory, it did, and Heisenberg was beginning to show quantitatively how to understand that. Heisenberg at first believed that the uncertainty that resulted in making different kinds of measurement, like position and momentum, that you could never get an exact position and exact momentum at the same time, was a matter of disturbance, that when you measured the momentum of a particle, that disturbed its position. Or when you measured its position, you disturbed its momentum. You hit it with a photon that was high energy to get its exact position, and that gave it a kick in some direction. But Niels Bohr did not like that. He thought that Heisenberg was onto something very important with his new mechanics of arrays, with his matrix mechanics. But he thought the understanding of this uncertainty, this inability to have a complete description of momentum and position at the same time, had nothing to do with this physical disruption. And they argued back and forth about the nature of this. It was something that went on for a very long time. Bohr just didn't like this idea of a disturbance theory being central to this idea of uncertainty. A better way of understanding this, one that came out of these discussions, is really something very fundamental that could even be understood with music or noise. You see, any signal, any musical song that you're used to seeing its representation graphically on a computer music program, for example, can be broken up into a combination of pure sound waves, of nice, smooth sine waves of different frequencies. If you had a piano that had an infinite number of keys, where each key was a different frequency and a pure frequency, you could combine these to synthesize any sound at all. The sound of a clap, or the sound of a song, or the sound of a door scraping on the carpet. You can always synthesize any waveform by a combination of pure tones. For example, a square wave could be thought of as having a certain frequency. And we start our synthesis by taking a nice, pure sound wave of the same frequency. And then we subtract a third of a wave that's 3 times the frequency of that fundamental, nice, smooth sine wave. Then we add a fifth of the amplitude of 5 times the frequency. Then we subtract a seventh of the 7 times that frequency, and so on. And the more we do this, the closer we come to creating the square wave that we were trying to make. And that's true for any waveform. We can always see a waveform, however complicated, as the combination of different pure tones. Now, a particle can be thought of as a wave packet, that is to say, a wave that's sort of zero and then is located in space and then zero again. And if we think of it that way, we can make up that particular waveform of flat, oscillation, flat, by a combination of pure tones. So, for example, if I had a clap of my hands, I could imitate that sort of pulse of sound, and I could simulate that by a different combination of pure tones, such that it would cancel itself out outside a small region, and I would essentially have made a packet, a wave packet of sound. Well, that's true for a particle as well. If we think of a particle like an electron as being a wave packet, the wave packet is a combination of different waves. Now you say, are we breaking the packet down? No, that's really all it is. I can make something that sounds exactly like a clap by a combination of pure tones. The combination of pure tones that makes up the single pulse of sound is the same thing as that clap as the sound propagates across the room. And that's what's true in quantum mechanics too. So if we think of things this way, if we say that a particle that is located in space, that acts like a particle, is actually a combination of different frequencies, then, recalling what de Broglie had taught us, that every pure tone, every pure frequency corresponds to a different momentum, then we can say that an electron located inside a teeny tiny thimble, in fact, is the combination of every different momentum. So it's not that we don't know its momentum. What's true is that when you locate a particle in a tiny region of space, it actually is a combination of all the different momenta. And if you prepare an electron in a pure state of momentum, that is to say a single frequency extending out infinitely, like the analog of playing a pure middle C on your piano, then where is that wave? Where is an infinite wave of middle C? It's everywhere. So if you choose to prepare your sound as a pure tone, it's located everywhere. It's pure in momentum and delocalized in space. If you prepare it localized in space, like a clap, like a single wave packet, then it's composed of all of the different frequencies and therefore has all the different momenta. So this is really the fulfillment of Bohr's original intuition that it's not a question of disturbance. It's really a fact about waves. If you have a localized wave packet, you need all the different frequencies to make it up. If you have a pure frequency, you need an infinite space in which that wave train can extend in different directions. That's what the uncertainty principle is really about. It's about the behavior of waves, and that every pure frequency corresponds to a pure momentum. To add up all of the different momenta gives you a localized position of the particle in space. And if the particle has a pure momentum, then it's completely delocalized in space. And if it's in between, you say the electron's just in a big box, then we can use a smaller number of frequencies to make it up, and it has some spread of frequencies, therefore some spread of momenta, and some spread of position. That's what's really going on in the uncertainty principle. So let's conclude. The uncertainty principle is not about interference. It's simply about the relationship of the spatial localization of a wave packet and the localization of the distribution of frequencies that make it up. The more localized in space, the more spread out the number of frequencies and therefore momenta have to make it up. In quantum physics, frequencies correspond to momenta. Each frequency of an electron, say, corresponds to a different momentum. That's all. So if a particle is localized in space, it is spread out over many momenta. If it has one momentum, then the wave is spread out in space. That's what's going on.